Good day, Madam Anita, and to all my friends. We are from Group 7, and the topic given to us is about tree and searching. So first of all, I would like to introduce myself. My name is Chong Wen-Jian Isaac, and my metric number is 207545. So first, I would like to share about the properties of tree. So for a tree, first property, there is one and only one path between every pair of vertices in a tree. Second, it has no loops and multiple edges. Third, for all vertices in the tree, it is connected, and for each pair of vertices, it is connected by only one edge. And last, a tree with n vertices will have n minus 1 edge. Okay, let's look at some examples. So for first diagram, it is a tree because we know that every vertices are connected by only one edge, no loops, and then for every single pair of this vertex, okay, it has only one path. So this is a tree. For a second diagram, it is not a tree because obviously we can see that these two vertex is not connected by an edge. Okay, and then okay, so for the third diagram, we can see that there is 7 vertex, so each will be n minus 1. So it will be 6 edges. 1, 2, 3, 4, 5, 6. And for the last diagram, it is not a tree because we can find that not every single pair of vertices have only one path. So for example, if I want to move from this vertex until this vertex, I can move like this, and I also can move like this. So it is not a tree. So next, we will look into the properties for M-array tree. So for a full M-array tree with I internal vertex, it will contain n equals to mi plus 1 vertices. And I know that it looks like very complicated, but we will look in by using an example later for us to know more about these properties. And the last one, there are at most m power h leaves in an M array tree with a given height of h. So based on the properties in the previous slide, in this diagram, it is a full 4 array tree. So m is equal to 4. So how many internal vertex in this tree has? It has 1, 2, 3. So I is equal to 3. So for this full 4 array tree with 3 internal vertex, it will have n equals to mi plus 1 vertex in total. So 4 times 3 plus 1, n equals to 13. And we know that n is the total numbers of vertexes. It includes I, the internal vertex, and the leaf as well. Therefore, we know that the leaf in this tree will be 13 minus 3. So equals to 10. And it will have a maximum number of leaves, which is m power of h, where the h is from A until F. It has 2 edges connected, so h will be equal to 2. So 4 squared equal to 16. So it will have a maximum number of 4 leaves. It will be holes in this tree. So at C you can add another 4 and E as well. So it will still be a full 4 array tree. So that's all from me about the properties of tree. Thank you, and I will pass to the next presenter.
Okay, it's my turn. My name is Zhang Xinmin. My metric number is 205016. Today, I want to present the spiny tree. First, we can know the definition. Let G be a simple graph. A spiny tree of G is a subgraph of G. That is a tree containing every vertex of G, which includes all the vertices of graph, with a minimum possible numbers of edges. What's more, a connected graph has at least one spiny tree. But how to get a spiny tree? It is easy. A tree with n vertices has n minus 1 edges. For example, like this picture, edges of this graph equals 2, so edges in minus 3 equals 3. Thus, the fastest way to get a spiny tree is just remove edges that form a simple circles. However, the spiny tree has many forms. Total number of spiny trees is n multiplied by different value of n minus 2. So total number of this spiny tree is 4 multiplied by difference value of 4 minus 2 is equal to 16. There are few spiny trees that we make, like this one. As for the minimum spiny tree, a minimum spiny tree in a connected weighted graph is a spiny tree that has the smallest possible sum of the weights of its edge. A weighted graph is a graph in which each branch is given a numerical weight. A weighted graph is therefore a special type of labelated graph in which the labels are numbers, which are usually taken to be positive. There is an example. This one is a weighted graph. Each branch is given a numerical weight. There are many spiny trees, but we should consider the spiny tree with the minimum sum of weight of each tree. So we choose this one. This one, the sum of edges equals to 7. What's more, we can find the minimum spiny tree by using more structured way. The first one is primeless algorithm. There are 4 steps of this algorithm. The step 1 is to choose a vertex randomly. The step 2 is select the nearest edges. Then we should find all the edges that connect the tree to a new vertex. Find the minimum and add it to the tree. Finally, repeat the step 3 until you have a spiny tree. The next one is a classical algorithm. There are 3 steps of this one. Step 1 is choose the edge with the least weight, which is equal to 1. Then we should take the edge with the lowest weight and add it to the spiny tree. If adding the edge created a cycle, then reject this edge. Finally, keep adding edges until we reach all vertices. Okay, that's all for me. I will pass it to the next person. Thank you.
Hello everyone, my name is Li Xiang with metric number 206537. Today, I'm going to present about the traveling salesman problem. First of all, we need to know what is traveling salesman problem. The traveling salesman problem, or TSP in short, is the challenge of finding the shortest yet most efficient route for a person to visit each city exactly once and return back to their origin city. And this is the photo of an example of the TSP. It is an NP-hard problem in combinatorial optimization, important in theoretical computer science and operations research. There are obviously a lot of different roads to choose from, but finding the best one, the one that will require the least distance or cost, what mathematicians and computer scientists have spent decades trying to solve for. And we need to know Is it really important in our daily life? I would say yes. There are a lot of application of TSP in our daily life. For example, they are drilling. It can be used in drilling printed circuit board, X-ray crystallography, computer wiring, overhaul gas turbines engines, routing vehicle, and also order picking problem in warehouse. So we can see there are a lot of use of TSP in our daily life. Then how to solve TSP? The problem can be solved by analyzing every round road, trip's road, to determine the shortest one. There are several approaches to solve this question. For instance, there are brute force approach, branch and bound method, and also the nearest neighbor method. This is the example that I will give on in how to solve this kind of question. This is the photo of the problem, which is this is the diagram, and this is the metric that we will use to determine the cost from a place to another place. Given the following diagram, trying to solve the following TSP. For this case, we are going to use the brute force approach. It is also known as the naive approach. It calculates and compares all possibility permutations of roads or path to determine the shortest unique solution. To solve the TSP by using this approach, we must calculate the total number of roads and then draw and list all the possible roads. Calculate the distance of each road and then choose the shortest one. And that one will be the optimal solution. And now I will do it step by step. First, we need to choose any point on this question as the origin. We need to choose whether we will start from 1, 2, 3, or 4. For this question, I've chosen 1 as our origin, and we need to construct a table from the origin to each city once and back again to the origin. For this, you can construct like this. 1, you can go to 2, 3, or 4, and then you back to 1 and construct like this. And then from diagram, we will know that there are 6, 7 ways to back to origin. And then we calculate the cost of each path. And then we know that 1 to 2, 2 to 3, 3 to 4, 4 back to 1. So I will write like this. And then we calculate, sum up all the costs. Why we will get 10? Because from 1 to 2, how to see this metric? From 1, we need to go to 2, so it is 10. And then we need to go to 2 to 3, 2 to 3. So we know that it is 9. So we sum up all of this. And then from here, after we complete all of this summation, we will choose the shortest one, which is the shortest one is this. It only costs 35. So from this, we know that the shortest path is 1 to 2 to 4 to 3 to 1 because the cost is lowest, which is 35. That's all from me. Thank you. Now I'm going to present about the tree analysis of sorting algorithm. First, we need to know what is tree sort. Tree sort is a sorting algorithm that is based on binary search tree data structure. It first creates a binary search tree from the elements of the inputs list or array, and then perform an in-order transversal on the created binary search tree to get the element in sorted order. Here's a step how the algorithm will work. Step 1, take the element input in an array. Step 2, create a binary search tree by inserting the data items from the array into the binary search tree. And step 3, perform in-order transversal on the tree to get the elements in sorted order. That's all from me. I'll pass to the next person.
My name is Eva Farzana binti Suhaimi and my metric number is 205975. So now I'm going to explain about application of trees and searching. In this topic, we will discuss 3 problems that can be studied using trees, which is How should items in a list be stored so that an item can be easily located? What series of decisions should be made to find an object with a certain property in a collection of objects of a certain type? And how should a set of characters be efficiently coded by bit string? The first one is binary search tree. A binary search tree is a binary tree in which each child of a vertex is designated as a right or left child, and no vertex has more than one right child or left child, and each vertex is labeled with a key, which is one of the items. Vertices are assigned keys so that the key of a vertex is both larger than the keys of all vertices in its left subtree and smaller than the keys of all vertices in its right subtree. In this example, we are going to form a binary search tree for the words mathematics, physics, geography, and so on using alphabetical order. So, the first one is the word mathematics, so we make it as the key of the root. Second one is the word physics. So physics came after the word mathematics, so we add a right child of the root with the key physics. And the third one is geography, and it comes before mathematics, so we add a left child of the root with the key geography. And the next one is zoology. Since it came after math and physics, so we add a right child of the vertex with the key physics and assign it the key zoology. And the rest of the process is the same. Next is decision tree. A decision tree is a rooted tree in which each internal vertex corresponds to a decision with a subtree at these vertices for each possible outcome of the decision. The possible solution of the problem corresponds to the path to the leaves of this rooted tree. In this example, we are going to form a decision tree that orders the element of the list A, B, and C. First, we need to compare A and B. There are two possible cases, which is A is greater than B and A is lesser than B. If A is greater than B, we need to compare A and C. And there are two possible cases, which is A is greater than C and A is lesser than C. If A is greater than C, then we once again need to compare B and C. And there are two possible cases, which is B is greater than C and B is lesser than C. And if we take this path, so it equals to A is greater than B and B is greater than C. The next is prefix codes. Prefix codes is an encoding where the bit string code for a letter never occurs as the first part of the bit string for another letter. It can be represented using a binary tree, where the characters are the labels of the leaves in the tree. The edges of the tree are labeled so that an edge leading to a left child is assigned O, and an edge leading to a right child is assigned A1. So this is the example, and the encoding for each leaf goes as this. So E is 0, A is 1, 0, and T is 1, 1, 0. So N is 1, 1, 1, 0, and S is 1, 1, 1, 1. So it can also be used to decode a bit string. For example, consider the word encoded by this bit string. So 111. So 1111 and it leads to S. And 10 it leads to A. 1110 leads to N and 0 leads to E. So the original word is sane. And the last one is game trees. Game trees can be modeled where the vertices of these trees represent the position that a game can be in it as it progresses, and the edges represent legal moves between these positions. When the game is in a position at an even level, it is the first player's move, while if it's at an odd level, it is the second player's move. The leaves of a game represent the final position of a game. In this example, we will construct game trees using tic-tac-toe. In A, by considering symmetric position equivalent, we only need to consider three possible initial moves, which is this one, and it continues to expand. And in B, shows a subtree of this game tree leading terminal position, where a player who can win makes a winning move. So, in this example, this is the final position of this game tree. So that's all from me and our group. Thank you.